Hello again. In this video, I'd like us to look at the atomic structure of metals. Now, in the previous video, you learned about the outer valence bands on the various atoms. And for metals, I'd like to look at possibly 3 or 4 varieties. Can we start with an atomic number Z equals 29, which we know, of course, copper, very useful metal in especially electrical engineering. Copper, its chemical symbol Cu. It fills the inner bands first of all from the nucleus outwards. I'm not going to list them all, you can see them all elsewhere. But in the outer band we have, when n equals 4, we have 4s to the 1. So there is one electron in the first band, the first inner band of the fourth shell. Okay, and that is a very useful valence electron. Okay, so it's available for sharing with other elements, or it's, as we'll see, available in what we call a sea of electrons within the metal structure. We have another useful metal conductor with an atomic number 47, which means, of course, it has 47 protons in the nucleus and 47 electrons orbiting normally if it's neutral. This is silver. With chemical symbol Ag, it has structure in the shells, which we know about. And at the end, the far end, we have 5s to the 1. So in the fifth shell, on the innermost shell, there is one valence electron. And another one I'd like us to look at, atomic number 79, which you may know as gold, symbol Au. Okay. The electrons build up in the shells. The outermost shell is 6s to the 1. Now you may notice something strange about these three metals. There's always a new shell formed on the outer bounds, if you want to call it, of the electron mist, the sphere of electrons which surround the nucleus. So a new shell in 4, a new shell in 5, a new shell in 6, each one has one free electron. And that's quite important in terms of conductivity, which we'll look at shortly. Okay, let me just draw you a scenario where we have a lattice of atoms. This could be copper or silver or possibly gold. Maybe I could draw 15. They should all be the same size, by the way. Okay, so I'm drawing a metal bar, if you will. Okay, so 10, 11, 12, 13, 14, 15, just purely arbitrary number. And maybe I could use red to indicate that this is a positive metal atom. In other words, it's an ion. Okay, and what that means is, say for example, it could be copper. So the outer electron has been stripped away from the atom. Therefore, the atom is no longer neutral. It's missing a negative charge, which means it's therefore positively charged. Okay, so, and all of these will have that outer electron stripped away. So these are all atoms, ions, positively charged. Okay, let me see if I can find a contrasting light color, because I'm going to draw some electrons in here now. Okay, here's one. It's not to scale. The electrons are a lot smaller than the nucleus. Here we go. Here, one there, one there. This is all totally random, so don't worry too much about where I'm placing them. Maybe put a couple here, a couple there, one here maybe, one there, one there, one there. Maybe that's enough. Okay. Now then, there's a couple of things to notice here about this lattice structure on the metal. Maybe I could use yellow here. So what can we say here? This is a metal ion. In other words, a positively charged atom. Positive shorthand, charge. Okay. Here we have, well, that and its friend and all of its friends is what we call a sea of electrons. These are electrons which have escaped the outer orbits of their metal atoms and have become detached, therefore detached from the outer shell of the host atom. So, in other words, the atom which originally hosted each individual electron. Okay, so how does this piece of metal stay together? Why does it not just disintegrate, perhaps like a liquid? Well, we're not dealing with covalent bonding here. We're dealing with, importantly, and I'm going to write it in a different color, metallic bonding. Okay, so it's not covalent, as you saw earlier, it's metallic bonding. And metallic bonding is caused by interactions between these transient electrons here and the metal ions. And there's interaction as the electrons move from left to right and all over the place at random. They interact with the ion which it is passing close to at the time. It could be any particular ion, and that will cause bonding to take place. Okay, metals are good conductors for those reasons, really, because it's the availability of the electrons. If I put a big positive charge over here, say, draw it that way, and a big, maybe change color to like green, so a big negative charge over there, then, well, yep, the nuclei, the center of the atoms, these things here, are too large to be mobile, but the electrons are definitely mobile, and they are going to switch color, all want to drift, because electrons are negative, of course. They're all going to want to drift in that direction. I'm not going to draw arrows on all of them. Hopefully you get the idea. They all want to go to drift towards the end which we've made positive, and that's essentially how electrical current is formed. Okay, maybe I've just got a little bit of space on the top right here because I would like to stick with white, and we want to talk about the conductivity of various metals. Okay, just to finish off. So number one, top of the pops is silver. Silver has a conductivity of around 6.3 times 10 to the 7 space Siemens per meter. Okay, that is the best conductor. Second in the list, we have copper. Copper has a conductivity of around 5.98 times 10 to the 7 Siemens per meter. Third in the list is gold with a conductivity of 4.52 times 10 to the 7 Siemens per meter. Lastly, there are other metals, but I'm just going to talk about 4 at the moment. Fourth is aluminium. You maybe think of aluminium foil that you may have at home. So aluminium has a conductivity of 3.5 times 10 to the 7 Siemens per meter. So the best, the highest conductivity is, of course, up here, silver. We don't make cables out of silver, of course, because that's very, very wasteful. Copper is the best metal to use in terms of cabling and wiring, etc. Printed circuit boards, what have you. Okay. You might be wondering then, so if we have here for silver 5s to the 1, okay, and yet here for gold we have a layer which is even further out and therefore higher energy, one might expect, therefore, why is not gold a better conductor than silver? In other words, rephrase the question in terms of conductivity. So why does gold have a lower conductivity than silver? Surely it should have a higher conductivity. Well, the key to that is this number here. Okay, so if we're talking about, perhaps this might be a silver atom here. Let me just shade that in for you. Silver atom. Gold atom is actually going to be larger because there are more protons in the nucleus and there are more neutrons. So the whole thing itself, including all its orbitals, is quite a bit larger than silver. And so if you've got all these things going on, it's a little bit more difficult for all the electrons to get through these gaps. And that's the reason why silver is a better conductor than gold. Okay. Hopefully that's been useful. Thanks for watching. See you in the next video.